All right, welcome back to the deep dive. Today we're diving into something that seems so basic, almost like we shouldn't need to talk about it. But honestly, it's one of those foundational skills that can really make or break your code and even, I think, how you come across in a technical interview, especially for those senior level roles. We're talking about how programs interact with the outside world, how they take in information and then present results back, in a way that actually makes sense.
You're absolutely right. And, when I'm interviewing candidates for senior engineering positions, the way they approach input and output operations often tells me a lot about their overall understanding of software design. It's not just about getting the job done. It's about doing it well. It's about writing robust and understandable code that can handle whatever the real world throws at it.
Right. It's like the difference between just building a house that stands up versus one that's well-designed, energy efficient, and, actually pleasant to live in. So for this deep dive, we're really focusing on two core aspects of input and output, especially in the context of a terminal environment, which is where a lot of developers spend their time. First, we'll look at how to read input from the terminal effectively, and then we'll dig into how to format that output so it's not just a jumbled mess, but something that's clear and easy to understand. This is stuff that every developer should know, but honestly, mastering it can really give you a leg up, especially in those pressure cooker interview situations.
Absolutely. Let's start with reading input. So whenever a program needs to get information from the outside world, it often uses what's called the standard input stream. Think of it like a pipeline, a direct connection from your keyboard, for instance, into the program. In Java, this pipeline is represented by System.in.
Okay, System.in, got it. So what flows through this pipeline? What kind of information are we talking about here?
Well, at the most basic level, System.in deals with bytes. Bytes are like the atoms of digital information, the smallest units of data that a computer can work with. Now, while everything ultimately boils down to bytes, trying to read and process information byte by byte would be incredibly tedious and error-prone. It'd be like trying to understand a sentence by analyzing each individual letter's numerical code.
Right, that wouldn't be very efficient.
Yeah.
So how do we make sense of this stream of bytes? How do we turn it into something more meaningful, like words and numbers?
That's where the scanner class comes in. Think of the scanner as a specialized interpreter that can take those raw bytes from System.in and translate them into data types that we, as programmers, can actually work with things like strings, integers, and floating point numbers.
So the scanner is like a bridge between the low-level world of bytes and the higher-level world of human-readable data. How do we actually set up and use this scanner in our Java code?
It's pretty straightforward. To create a scanner object and connect it to System.in, you typically use a line like this: var_in, varins.in. This creates a scanner object named in and attaches it to that standard input pipeline, ready to process whatever the user types in.
Okay, so now we have our scanner ready to go. What kind of tools does it give us for actually reading different types of input from the user?
Well, it depends on what you're expecting from the user. If you want to read an entire line of text, maybe something like the user's full name, which could include spaces, you'd use the nextLine method.
So if the user typed in Jane Doe and hit enter, nextLine would grab that whole string, Jane Doe, spaces and all. What if you just wanted to read a single word, like just the first name?
In that case, you'd use the next method. This method reads input until it encounters what we call white space, things like spaces, tabs, or new line characters from pressing enter. So in your Jane Doe example, next would only read Jane because the space after it acts as a delimiter, telling the scanner, okay, that's the end of this word.
Got it. So nextLine reads everything up to a new line, and next reads up to the next white space character. What about reading numbers? How do we handle integers and floating point numbers?
For integers, whole numbers, we have the nextInt method. And for numbers with decimals, we use nextDouble. These methods try to interpret the input as the specified numerical type.
This is all making sense, but what if the user types in something unexpected? Like, what if they're supposed to enter a number, but they type in a word instead? Does that cause problems?
That's a great question, and it highlights a really important point about writing robust code. Before you actually try to read a specific data type using nextInt, nextDouble, or even nextLine, it's crucial to check if the input is actually of that type. Otherwise, you risk throwing exceptions and crashing your program.
Ah, right. So how do we do that checking? How do we make sure the input is what we're expecting?
The scanner class provides a set of hasNext methods for exactly this purpose. You have hasNextLine to check if there's another line available, hasNext to check for any token delimited by whitespace, hasNextInt to check for an integer, and hasNextDouble for a floating point number.
So before we try to read an integer, we should always use hasNextInt to make sure there's actually an integer waiting to be read. Can you give us a quick example of how that would look in code?
Sure. You might have something like this. If in.hasNext age in.nextInt. Now you can safely work with the age variable. This if statement acts like a safeguard, ensuring that we only call nextInt if the next piece of input is actually a valid integer. If it's not, we might handle that differently, perhaps by prompting the user to enter a valid number.
That makes a lot of sense, like looking before you leap. Now, before we move on to formatting output, there's one thing I wanted to clarify. When we use the scanner class, do we need to do anything special to make it available in our Java program?
Yes, good point. The scanner class isn't directly available by default. It lives in a package called java.util, which contains a bunch of utility classes. So to use the scanner, you need to include an import statement at the top of your Java file. Import java.util scanner. This tells the compiler, hey, I want to use the scanner class from this utility package.
It's like telling a librarian which section of the library you need to access. Okay, so we've covered the basics of reading input using the scanner. But what about situations where we need to be extra careful about security, like when reading sensitive information like passwords? Is the scanner still a good choice then?
That's a really important consideration. When it comes to passwords, the scanner isn't ideal because the input is visible in the terminal as the user types it, which is a major security vulnerability.
Right, you wouldn't want someone looking over your shoulder or a malicious program logging your keystrokes to see your password in plain text. So what's the more secure way to handle such sensitive input?
In those cases, we can use the console class. It provides a more secure mechanism for reading input, especially passwords.
Okay, console class, got it. How do we get a console object in our Java program?
You'd typically use a line like console terminal system.console. However, there's a bit of a caveat here. If you're running your code within an IDE, the console object might not always be available, depending on how the IDE simulates a terminal environment. This is something to be aware of during development. In a real production environment, like a server, you're more likely to have access to a proper console.
So it's a potential gotcha to keep in mind, especially during development.
Yeah.
Assuming we do have a console object, how do we actually use it to read input securely?
For reading things like usernames, you could use the readLine method, which is similar to the scanner's nextLine. But for passwords, the key method is readPassword. This method is designed with security in mind. It doesn't echo the characters as the user type, so the password remains hidden.
That's good, so no one can snoop on the password as it's being entered. But is there anything else special about readPassword? Does it return the password in a particular way?
Yes, and this is a crucial detail. ReadPassword returns the password not as a string object, but as a char array, an array of characters.
I see. So why is it important that the password is stored as a char rather than a string?
In Java, string objects are immutable, meaning once they're created, their content cannot be changed. This immutability is generally a good thing for security, but in the case of passwords, it means the password could potentially linger in memory even after you're done with it, increasing the risk of exposure.
Ah, so the password could be sitting in memory, vulnerable to attacks even after the program is seemingly finished using it.
Exactly. Now, a char array, on the other hand, is mutable. This means you can explicitly overwrite the contents of the array after you've used the password, essentially wiping it from memory. This practice of minimizing the lifetime of sensitive data in memory is a fundamental security principle.
So by using a char, you're reducing the window of vulnerability, making it much harder for attackers to steal the password. That's really clever.
It's all about thinking defensively and minimizing the attack surface. Now, before we move on to formatting output, I want to briefly mention another way to handle input and output, especially when dealing with files rather than direct interaction with the terminal.
Okay, this is getting interesting. So far, we've been focusing on real-time input from the user typing at the terminal. What other ways are there to get information into a program?
Well, Java, like many programming languages, allows you to redirect where a program gets its input from and where it sends its output. You can do this using commands in the shell, the command line interface. For example, you might encounter commands like javamypackage.mainClass, input.txt, output.txt.
Let's break that down. What's happening in that command?
The input.txt part is telling the Java program to read its input not from the keyboard, but from a file named input.txt. And the output.txt part is saying, instead of printing the output to the terminal, write it into a file called output.txt.
So you're essentially controlling the flow of information at the operating system level, redirecting the input and output streams to different sources and destinations. That's powerful.
It is. This technique is particularly useful for automating tasks, for testing your program with predefined input, or for processing large amounts of data without requiring manual user input. Imagine you have a program that processes 1 million records from a database. You wouldn't want to type those in manually at the terminal.
Definitely not. So input redirection allows you to feed that data directly from a file, and output redirection lets you capture the results in another file for later analysis. That's much more efficient.
Exactly. However, it's worth noting that this kind of redirection is happening at the shell level. If you want to do more sophisticated file handling within your Java code, like reading specific parts of a file or writing data in different formats, you'd need to use other parts of the Java API, which we might cover in a future deep dive.
Got it. It's like the difference between having someone deliver a package to your doorstep versus going inside and organizing the contents of the package. Different tools for different levels of interaction. All right, so we've covered quite a bit of ground on how Java programs take in information. Now let's shift our focus to the other side of the coin, how to present information back to the user in a clear, structured way. We've already touched upon System.out.println, which is probably the first output method most Java developers learn.
Yes, System.out.println is the workhorse for basic output. It takes whatever you give it, whether it's a string, a number, or even an object, and prints it to the terminal, followed by a new line character, which moves the cursor to the next line.
And we also have its sibling, System.out.print, which does pretty much the same thing, but without adding that trailing new line.
Precisely. System.out.print is particularly useful when you want to display prompts or construct output incrementally, where multiple pieces of information appear on the same line.
For example, if you wanted to prompt the user for their age, you could use System.out.print, your age, and then read the input using in.nextInt. The user's input would appear right after the colon on the same line.
Now, one thing you might have noticed when using System.out.print or System.out.println to display numbers, especially those with decimal places, is that the output can sometimes be a bit messy. It might include a lot of digits after the decimal point, which isn't always what you want.
Right, like if you were displaying a price or a financial calculation, you probably wouldn't want to show 10 decimal places. You'd want to control how many digits are displayed and maybe even add things like commas for thousands separators. Is there a way to do that in Java?
Absolutely. For more fine-grained control over the appearance of your output, you have the Printf method, which stands for formatted print. Printf allows you to define precisely how your data should be presented using a special string called a format string.
Format string. Okay, so how does this format string actually work? Can you give us a concrete example?
Sure. Let's say we wanted to print the result of dividing 1000.0 by 3.0, but we only want to display 2 decimal places. We could use System.out.printf, Part8.2f, format mul 3.0. The format string here is %8.2f. Let's dissect it.
Yes, please. I'm curious to see how this magic works.
The percent symbol is like a signal indicating the start of a format specifier. The 8 that follows specifies the minimum field with the total number of characters the output should occupy. So in this case, we're saying the output should take up at least 8 characters, even if the number itself is shorter. The .2 defines the precision, which, for floating point numbers, means we want to display exactly 2 digits after the decimal point. And finally, the hef is the conversion character, telling print that we're dealing with a floating point number.
Okay, I think I'm starting to see how this works. So what would the output of that line of code actually look like?
You'd see 333.33. Notice the 2 spaces before the number. That's because we specified a field width of 8, and the formatted number only takes up 6 characters. By default, print, right, justifies the output within that specified field width, hence the leading spaces. This alignment can be really important when you're generating reports or tables where you want things to line up neatly.
That makes perfect sense. So you're not just controlling the number of decimal places, but also how the output is positioned within a certain width. That's pretty powerful. Now, what if you wanted to print multiple pieces of data on the same line using Printf? Can it handle that?
Absolutely. You can include multiple format specifiers within a single format string, and each one will correspond to one of the arguments you pass to printf after the format string. For example, System.out.printf. Hello, percents. Next year, you'll be proceed, ds, name, age. Here, percents is a format specifier for a string, and proceed is for a decimal integer. The n at the end is the new line character, so the next output will start on a new line.
So if the name variable held the value Alice and the age variable was 30, that line of code would print, hello, Alice. Next year, you'll be 31, followed by a new line. That's much cleaner than trying to concatenate strings manually using plus signs.
Exactly. Now, what's really cool about print is the wide range of conversion characters you have at your disposal. For integers, besides the standard decimal format D, you also have X or X for hexadecimal, base 16, and O for octal, base 8. These are particularly useful when you're working with low-level system information, bitwise operations, or debugging.
So you could print the same integer value in decimal, hexadecimal, and octal using different conversion characters. That's a handy tool for developers working close to the hardware or with binary data.
Precisely. For numbers with decimal places beyond the F format we saw earlier, you also have E or E for scientific notation, G or G for a general format that automatically chooses between F and E based on the number's magnitude, and even A or A for hexadecimal floating point representation, which is more specialized.
And for text, we have S or S for strings and C or C for individual characters. Are there any other conversion characters we should know about?
You also have B or B for Boolean values, H or H for displaying hash codes of objects, percent for printing a literal percent symbol, and percent for a platform-independent newline character, which is generally preferred over N for portability.
Wow, that's a pretty comprehensive set of formatting options. But the customization doesn't stop there, does it? There are also those flags you mentioned earlier.
Yes, the flags. They provide even more granular control over how your output is presented. You can use flags to control alignment, padding, whether to include signs, how to handle negative numbers, and much more.
And can you give us a few examples of flags and how they affect the output?
Sure, the plus flag will always display a sign, even for positive numbers. So instead of just 3333.33, you'd see plus 33333.33. The space flag adds a leading space before positive numbers, which can help align positive and negative values, especially if you're using the flag to enclose negative values in parentheses, which is another flag you can use.
So with the flag, a negative number like -1234.56 would be displayed as 134.56. That's a common convention in financial reporting. What about controlling alignment within the field width? We saw how the default is right justification. Can we change that?
Yes, you can use the flag to left justify the output within the specified field width. The zero flag is interesting. It adds leading zeros instead of spaces to fill the field width. This is often used for formatting dates or times, like '09 instead of 9 for a single-digit hour.
And for those large numbers where you'd want to add 1,000 separators to make them more readable, there's a flag for that too, right?
Absolutely. The zero flag adds those locale-specific grouping separators, like commas in English. For floating point numbers, the hashtag flag forces the inclusion of a decimal point, even if there are no fractional digits. And for hexadecimal or octal integer formats, the hashtag flag adds the 0x or 0 prefix, respectively, making it clear which base is being used.
Those hashtag flags seem particularly helpful for avoiding ambiguity. Now, there are a couple of flags and serials that look a bit more advanced. What do they allow us to do?
The flag is for explicitly specifying which argument a format specifier should be applied to. It's useful when you need to format the same argument multiple times, or when you're dealing with a large number of arguments and want to be extra clear. The flag is the clever one. It tells print to use the same argument as the previous format specifier. This can save you some typing and make the format string more concise when you need to display the same value in multiple ways.
So if you had print_percents and you passed a single integer argument, it would be printed first in decimal and then again in hexadecimal. That's pretty neat. Can you give us an example that brings together a few of these flags?
Sure. Remember our division result earlier, which was roughly 33333.333. We could format that like this. System.out.println, %, plus 0.2s, 0.0.0.03.0, which would output plus 33,333.33. Notice the comma for the thousands separator, the plus sign indicating that it's a positive number, and the 0.2f for 2 decimal places in fixed point format.
That's a great illustration of the level of control you have with print. Now, before we wrap up, I want to ask about one more thing. Is print the only way to create formatted strings in Java?
There's also the formatted method, which is a more recent addition to the language. It uses the same format string syntax as print, but instead of directly printing the output, it returns a formatted string as a string object.
That makes sense. So you could use it like this. String message, hello percents. Next year, you'll be %dn, formatted, name, age. And then you can do whatever you want with that message string, whether it's printing it later, saving it to a file, or using it in a graphical interface.
Exactly. It provides a clean separation between the formatting logic and the actual output operation, which can make your code more modular and easier to test.
Awesome. So we've covered quite a lot today about input and output in Java. For our listeners who are preparing for those senior-level technical interviews, let's quickly summarize the key takeaways.
When it comes to reading input, remember the scanner class for parsing various data types. Always use the hasNext methods to check for the availability of the expected input type. For sensitive information like passwords, use the console class and its read password method, which returns a mutable char for security. And remember the concept of shell-level redirection for interacting with files.
On the output side, System.out.println and System.out.println are your basic tools. For more precise formatting, use Printf with its format strings, conversion characters, and flags. And don't forget about the formatted method for creating formatted strings that you can use later.
Remember, these fundamental I/O operations are not just about making a program run, they're about writing code that is reliable, secure, and communicates effectively with the user or other systems. Demonstrating a solid understanding of these concepts shows attention to detail and a commitment to best practices, which are hallmarks of a senior engineer.
Absolutely. So, as a final thought, consider how thoughtful input handling and clear output contribute to the overall user experience and the maintainability of your code. Think about situations where these seemingly simple concepts can make a huge difference.
It's about thinking beyond the immediate task and understanding how your code interacts with the world around it. These are the kinds of insights that distinguish senior engineers from junior ones.
Well said. Thanks for diving deep with us today. We'll catch you next time on The Deep Dive.